would you put for that? Is it a mixture or a pure substance? Okay, so when you look on the periodic table, you see gold is AU, but 10 karat gold tells you the amount of gold compared to other metals. So 10 karat gold, 14 karat gold, 18 karat gold, 24 karat gold is the highest gold content, but pure gold is so soft it would bend. So this gold, in order to make jewelry with it, you have to mix it with other metals. So if it's mixed with other metals, this is a mixture. So this is a mixture, but when you look at it, is it homogeneous or heterogeneous? Oh, so you can't see like the copper in it. You can't see the zinc. Okay, so when they talk about the carat value, that is telling you how much gold compared to the other metals that are in it. How about salt water? It's a mixture. Okay, and is it homogeneous or heterogeneous? Oh. Oxygen gas, pure substance. It is a pure substance because oxygen's on the periodic table. And so is that a element or a compound? Element. Unstirred paint. So if you've gone to the store, if you've gone to Lowe's and you buy paint and it's not stirred, when you open it up, what do you see? What do you see on top? Have you ever opened like an old can of paint? Yeah, there's like a liquid on top, okay? So paint, if you don't stir it, if it's latex paint, water comes to the top and the paint pigments start to settle to the bottom. If you buy oil-based paint, then it's oil that's on the top and it's the paint pigments on the bottom. So that means it's a mixture. And since you can see layers, it's heterogeneous. So ammonia gas, ammonia is NH3. So what does that make it? It's a pure substance. Is it an element or a compound? Compound. So remember, that's kind of the trick with identifying compounds. If you see a chemical formula and there's more than one element in the formula, then you know that it's going to be a compound. So the air in this room, is made up of nitrogen and oxygen, and then a whole lot of really small numbers of gases. So there's like water vapor, there's carbon dioxide, there's some argon in the air. So there's lots of really, really small concentration, but these are the two big ones. So that means that air is what? It's a mixture. So is it homogeneous or heterogeneous? Homogeneous, because you can't see it, right? You can't see any parts or layers. Now, if it's foggy, like this morning, some parts of this area had a lot of fog, that's water vapor that is actually condensing and you can see it. So then that would be heterogeneous, but just the air, generally homogeneous, you can't see those layers. And then the last one. So the last one, they have been paving 64 since like April. Like first they started working on bridges and now these like exit ramps, and finally one day I'm thinking they're going to finish. I'm not sure when it'll happen, if it's in my lifetime or not. But so asphalt is made of tar, rocks, sand is really what I meant in that. It's tar, rock, sand, and in fact very, very small amounts of glass. So you might notice sometimes in the evening, if you're driving, the roadbed actually has a little bit of reflectiveness to it. That is actually because they put very small amounts of crushed up glass to give that reflective property. So that means that asphalt is a mixture. All that stuff goes into the big asphalt maker, and it like lays it down, then they just roll it and roll it and roll it. Hopefully it's not bumpy for at least a week. I was driving on a paved part of 64 this morning, and it was like, I was already like bouncing. I'm like, this isn't even flat. It's like only been on the road for like maybe a month. Coming out of Tarboro, coming this way, I was like shocked. I was like, it's not flat. Like I could feel the car just doing this. It was craziness. All right, but is it homogeneous or heterogeneous? So if you look at asphalt, it's heterogeneous. You can see rocks in it. Okay, so these would be good examples of ones that I would ask. I won't ask you ones that you would have no idea. They would have to be stuff that we've talked about in class, things that you've seen in your dynamic study modules, that type of thing. So that's the being able to identify pure substance. Remember, if you see it on the periodic table, then you know it's a pure substance and an element. if you see a formula with more than one element, then you know it's a pure substance in a compound. But pretty much everything else is a mixture, and you have to think, is it homogeneous or heterogeneous? Okay, so then this kind of leads us into this discussion about the periodic table. So if you didn't grab a periodic table, hopefully you brought your unit conversions and balancing equations handout. So that would be, if you brought this one from last week, okay, the last page is a periodic table. And so this one, like, you can write on, because this one is yours for you. But do know that when you come in, you can always grab a periodic table. I always put the laminated periodic tables out. So when you come in, you can always grab one because, I mean, you can look over there, but it's always easier if you just have one to look directly at. So when talking about the periodic table, things about the periodic table, when we talk about the vertical groups are called, or the vertical columns are called groups, and groups have similar properties. So here's an example. The next to the last group, which is fluorine, chlorine, bromine, and iodine. All four of these elements actually have common characteristics. So chlorine, what do you use chlorine for? Swimming pool, okay? Because it has a disinfectant property. If you have ever had surgery, which of these have they scrubbed your skin with? Iodine, because again, antiseptic property. All of these have an antimicrobial, antibacterial property, so they're very good at treating areas or materials that you're trying to reduce the amount of bacteria. So bromine, you can actually buy bromine tablets. People put them in like hot tubs. And so it has the same effect as chlorine does. It's just a little more stable. So all of these, they're all in that same column. So if you look to the next to the last column on your periodic table, that says that they're in column 7A. They call these the halogens. And one characteristic of the halogens is that they are good antiseptics, antimicrobial agents. They help to keep microbes from being able to grow in water or being able to grow on surfaces. So that's an example of one of the group's columns. Another one that you can see if you go and look, it's number 29, 47, and 79. It's over on this one. If you find 1B, it's row 11, 11 rows across. Cu is copper, Ag is silver, and Au is gold. So all of those they use in making jewelry. They call those the precious metals. Used to be that like only people that had money were able to afford those types of things. And so that's where that name, but being in that column, they have similar properties. Things that go across are called the periods. So a period is a row going across. And one characteristic of the period, if you see the numbers above each of the symbols, as you go from left to right across, what happens to those numbers? They increase by 1. So like if you see H, which is hydrogen, there's a number 1 above it. If you go all the way across to He, which is helium, there's a 2. Then you go to the next row, which starts with lithium, there's a 3. Then beryllium, there's a 4. Then boron's a 5, carbon's a 6, nitrogen's a 7. So notice that those numbers increase as you go across. Another thing you can pick out immediately on looking at a periodic table is metals and nonmetals. So metals are everything that is to the left of the zigzag line. So looking at this periodic table, you actually don't see a zigzag line, but if you look at your periodic table, you can see that zigzag line. It is darkened. It starts underneath boron, which is number 5, comes down, and it's sort of this zigzag or staircase. And everything that is to the left is going to be a metal. So that means the majority of elements are metals. I like this periodic table in a way because this periodic table actually tells you the state they exist in. So everything black on this is a solid at room temperature. Everything that's red is a gas at room temperature. Anything that's blue is a liquid. So this one actually shows you solid, liquids, and gases. The ones that are in white, those are the ones that are unstable. They last for such a short period of time because they're man-made that they really don't get into a category of being a metal, a solid, a liquid, or a gas. So that's the ones that are kind of the white outline. Those are ones that like chemists make. They make them in they have to like smash atoms together in order to make them to form. But as soon as they make them, they start breaking down. They're not very stable. But looking at the black, the red, and the blue, most metals are what? They exist as solids, okay? So most metals are solid at room temperature because those are the black. Everything that's in black to the left of that zigzag line. So they're solids at room temperature. Most metals, you can shape them, right? So you can bend them. Some of them you can form into wires. And one characteristic they found is that metals will conduct electricity. So they can carry an electric current along their wires. So they're called conductors. So they will conduct electricity. Non-metals, looking to the right of the zigzag line, they're definitely in the minority. So if you're looking at the periodic table, everything this way is metal. So that's all of these and these two bottom rows. Those are all metals. Non-metals are just the small group up here in this upper right corner. So definitely these are in the minority. What would you say about them? Are they solids, liquids, or gases at room temperature? Most of them are gases. So see the red? See how everything on the far right column and then nitrogen, oxygen, fluorine, and chlorine are all in the red? So these tend to be gases at room temperature. So RT is room temperature. Gases at room temperature. The few that are solids, like carbon, phosphorus, sulfur, the ones that are black right there, those, though, they're really brittle. So if you tried to take carbon and crush it, it would just shatter. Same thing with sulfur and phosphorus. It's really like a powder. So you can't roll it. So it's not shapeable. So these instead, these are brittle. They can't be formed into a wire, and they're not conductors. They cannot carry electricity. In fact, they're pretty good insulators. Now, there is a group down at the bottom. The group at the bottom are the ones that you find right along the zigzag line. So the ones that are like silicon, germanium, astatine, arsenic, tellurium, all of these that run right along that zigzag line, they call them metalloids. And they got this name because they have some characteristics like a metal, some characteristics like a non-metal. So when you look, they're really just the ones right along this line. So looking at the zigzag line, because how they got their name, you know how things, sometimes if they're right at the in between, they're a little like each of them. We're not going to really talk about metalloids because they're not as common in the human body. Most of the ones that we're going to talk about, they're all just metals or non-metals. But just to mention that. So this is the periodic table that's in your book, okay? And so if you go to your e-text, remember I showed you last time, they're in the e-text down at the very end of the contents, that back matter. You can actually see this periodic table. I like it because everything that's purpley blue, those are metals. Everything yellow, non-metals. So see how many metals compared to non-metals you've got. And then you can see the green that run right along the zigzag line. Those are those ones that are kind of metalloids. You don't have to memorize which ones they are. But the big thing is just remember that zigzag line. That dark line, everything to the left is a metal. Everything to the right is a non-metal. So in terms of ones that you need to be familiar with, there are 118 known elements now. You do not have to memorize their names and symbols, okay? The only ones that you need to know are the ones that we will talk about over and over and over again over the course of the semester. So that includes elements 1 through 20. By saying 1 through 20, that is that number above the symbol. So it's really the first 20 across the top. So H is hydrogen, He, helium, then Li, lithium, Be is beryllium, beryllium, B is boron, C is carbon, then NO, F. Fluorine, everybody always thinks fluoride, so fluorine is its technical name, and notice that it's an F. I cannot tell you how many people put FL. You know what FL is? That is the abbreviation for Florida, okay? That is the state abbreviation, but I have people that do that like all semester long. If they put fluorine, they put an FL, and I'm like, it's just an F. So it doesn't have an L along with it. Then going across NE, it's used to make lights. It's neon, so neon. Now, the next one, when we get to 11, it's Na, sodium. And so all the ones up until here, it's like the first letter or the first two letters of the name. You're like, oh, that's not so hard to remember. But now we get to sodium. Well, it's because they had already named sulfur as S when they found sodium. So they went with the Latin word. So sodium, the Latin for it is natrium. So that's why it's capital N, lowercase a. Mg, magnesium, Al, aluminum, Si, silicon. P is phosphorus. And that's another one. So you'll see that one in a minute. S is sulfur. So I have people get S, they write sodium. Those are ones that are commonly like mixed up. And if that's you, like you may want to sit and write down the names and the elements, names, symbols, and just practice them a couple of times. Cl is chlorine. Ar is argon. Okay. Then 19 and 20 are on that third row. K is potassium, because that's another Latin term, which is kalium with a K. And so that's like if someone has hyperkalemia or hypokalemia, elevated or low potassium levels, that's where that name comes from, because that K comes from its Latin term. And then calcium is Ca. So that's 1 through 20. Okay, so you want to go through, practice the names and symbols. Notice that the first letter is always capitalized. If there's a second letter, it's always lowercase. So you would always write capital N, lowercase a. So then you've got 10 more. So all you have to learn is a total of 30. You probably know half of 1 through 20. You probably already know and have seen those like carbon, Ca, calcium. But these ones are the other ones. And the reason why is these are either we're going to talk about them in terms of their use, or they're part of the human body, or they have some kind of health importance. So Cr is chromium. And so you might, if you have your paper periodic table, like you could like either underline it or put a little star next to that one. I did them as I go across. So notice that Cr is number 24. Fe, that's another Latin term. So Fe is iron, comes from the Latin term ferrous or ferric. And Co, I have a lot of people think that that's copper, but that's cobalt. And Cu is copper, because that's a Latin term. So those ones are all going across that same row that potassium's in. Zinc is right after copper, and it's capital Z, lowercase n. And then if you go all the way over to the end, see bromine. So we have bromine Br, because bromine's in that halogen column. Ag is silver. So Ag is number 47, right underneath copper. And then underneath it is gold, which is Au. So we have copper, silver, gold, all in a column on the periodic table. Hg, where have you heard Hg? It's mercury, but where have you heard that? MMHg, what's that stand for? When you do, it's a unit for blood pressure. So MMHg is millimeters of mercury. So it's a way of measuring pressure. And so if you take someone's blood pressure and you say it's 120/80, that's 120 millimeters of mercury. over 80 millimeters of mercury as a pressure value. So that's the Hg is mercury. And then the one way up at the top, because I didn't think there was enough room down at the bottom. So there is I, and I added I. One, we're going to talk about iodine because we're going to talk about the thyroid. But then two, I is also in that halogen column, fluorine, chlorine, bromine, and iodine. And so we'll actually use it in building molecules. So we will talk about it again. So those are 10, 2, 4, 6, 8, 10. So you only have 30. Out of 118, you've got to know the names and the symbols for 30, 1 through 20, and then these 10. So their significance. And if you want to see this periodic table, remember that this is on, in that back matter, the list of the names and the symbols for the elements is the second slide in that back matter. And on the e-text at the very end of the contents has like, kind of like, I think of it as like an index and glossary and stuff like that. They actually do list all the names and the symbols for all the elements. So you could go through and find those just if you want to practice and make sure that you have the names right. So out of 118 elements, how many do you think are found in the human body? So looking at all of those, just estimate, half, quarter, all of them? What do you think? A quarter? They're pretty close, yeah. So there's really only about 23 elements found in the human body out of 118. So out of those, though, this chart really kind of splits them up. So the first one, the most common, I call these the main elements. And they are CHO and N, which to me sounds out Chon. So it's sort of like a little mnemonic way to remember. Carbon, hydrogen, oxygen, and nitrogen. These are the atoms that make up carbohydrates, lipids, proteins, nucleic acids. Okay, all of the building blocks for cells. So these make up 96% of the atoms in the human body. Just these four. Then we have the minor elements. Minor because they're not as high in concentration, but they are themselves very important. So this is Na, which is Mg, which is P, which is phosphorus, S, which is sulfur, Cl, chlorine, K, potassium, and then Ca, calcium. So the ones that are in orange up there, those 7 are called the minor elements. If you added all of their atoms up, they would make about 3.9% of the human body. So just 11 atoms make up 99.9% of you. Then the little itty bitty ones, okay? They call these micronutrients. I just say they're trace because they are found in extremely low concentrations. These have very specific functions. So you typically don't find these everywhere in the body. So for example, iron. If you don't have enough iron in your diet, you might end up being cold, yes, because that's a symptom of, begins with an A, anemia, right? So somebody that doesn't get enough iron in their diet ends up anemic because that means that you don't have enough red blood cells. So if there's not enough red blood cells, you don't have as much iron, oxygen carrying in the blood. And so your body cells don't get the oxygen they need. They can't do the metabolism they need. You can't generate enough heat. You feel cold and tired. And if you stand up really fast, what happens? Yeah, you're like, whoo, let me hold on to something. Okay, and that's all because of low oxygen. Because iron needs to be in those red blood cells to be able to bind oxygen. So that's really specific. So you don't find oxygen you don't find iron in your hair cells. You don't find iron in your skin cells. You find it in your red blood cells. So trace elements tend to be in very specific places. Iodine. We're going to talk about iodine in the next chapter. Who knows? There's only one group of cells, only one gland in your body where all the iodine you eat goes. Your thyroid. All of it goes to your thyroid. Your thyroid is this little gland. They're like two little lobes, not even like pecan size, right underneath your Adam's apple. So, you know, the piece that bumps out when you swallow. So there's two little glands and they're connected. They're right there. And all the iodine that you eat goes there. Doesn't go anywhere else. That is because your thyroid is where you make thyroid hormone. And thyroid hormone has iodine in it. So that is why it is concentrated there. So see how those trace, they're found in like really specific places. They have very specific jobs. You don't just find them scattered all over the body. So like zinc. Zinc is important in immune cells. So if you're sick, you might take some vitamin C with zinc and selenium added. Both zinc and selenium are trace elements, but they have been found to help support your immune system cells. So your white blood cells work better if they have enough zinc and selenium. So that's what I mean by a trace element. Just think of something that's like very specific, not found everywhere, so it doesn't have to be in very high concentration. Okay, and everybody knows fluoride is important in your teeth. Yep, that's exactly it. Pretty much that's where fluorine is found. Small amount in your bone, but it really helps to make your enamel resistant to breakdown. So it helps keep you from getting cavities, which is why you're supposed to brush your teeth with fluoride toothpaste. Okay, so those are not all of those, not all of them. Those are just some of the ones. I didn't list every single one of them, but the main and the minor are the big ones. You really should know CHM. Those are the main elements. And you should know the 7, sodium, magnesium, phosphorus, sulfur, chlorine, potassium, and calcium. Those are the minor. So we actually covered this. So we talked about the states of matter, like how matter is solids, liquids, and gases, and how those particles are different in terms of their spacing. A little bit about like shape and volume. Remember, we did this last time, talked about how those molecules are moving or their energy. So you can take ice, put it out on the table, and it'll melt, right? So you can go from a solid to a liquid. That is called a physical change because I can change it back, okay? So melting, boiling, freezing, all of those are good examples of what they call physical changes because does it change the water? No. The water is still water. It's still H2O. I haven't changed how it's arranged. So boiling, good examples of physical change. If I boil or melt, if I freeze. What if I take a piece of aluminum foil and I cut it in half? Is it still aluminum foil? Yeah. If I cut it into quarters? Yeah. If I cut it into confetti pieces? Yes, but don't put it in your mouth. Okay? So if you cut something, cutting, chopping. Okay? I've just made it a lot of little pieces. If I change the shape, roll it into a ball and then ball it up. That's all considered a physical change because in theory, I could like put it back. So I could take those pieces of aluminum and like melt them back together and they'd still be the same aluminum. But what's different is chemical changes. So there can be changes in molecules that I can't just make them back. So the example that they give you is what happens when you burn charcoal, right? So you start off with your black charcoal briquettes. You light them. Sometimes it requires some lighter fluid. So you light them, but then once they begin to light, they don't like just go back to their original. In fact, you get lots of heat released, and over time they change from being black to being gray. Okay? And then over time they start to look smaller. So those briquettes look like they're shrinking in size. And eventually, if you let them burn completely, it's nothing but like ashes left behind. Heat being released, seeing something that like disappears, but you can't get it back. So seeing heat, seeing flames. If you have something that bubbles, not necessarily boils, you haven't added any heat to it, but it bubbles. Like if you put peroxide on a cut, that's a chemical reaction that occurs. That bubbling takes place because of the reaction between the peroxide and the cut. Helps to get rid of, it helps to like eat any microbes, break them down that might be in that area. So those are examples. But the kicker is with this, we have changed the nature of the substance. It's not charcoal anymore. And so what we did is we actually did this. So the charcoal is here, and it's carbon. When we burn charcoal, we're combining it with oxygen. And it's forming carbon dioxide. So in this, you can recognize a chemical change because there's a chemical reaction that goes along with it as well. And a chemical reaction always has an arrow. This arrow goes from left to right. Everything that's on the left side is called the starting materials. Everything that's on the right side is the product. So the reactants are starting materials, what you have to begin with, and then the products is what you end up with. And they are not the same thing. So a chemical reaction occurred. So you would actually read this, it's like a sentence that would say that charcoal plus oxygen reacts to form carbon dioxide. Okay? Or carbon plus oxygen forms carbon dioxide. Either one of those, perfectly fine. Now notice after, in this, we're writing it out just based on their symbols. Do you have a question? Oh, okay. I was just wondering because you had your hand like that. So if you have it written out this way, they call that a chemical equation by using the symbols for the elements. And so notice it has C with an S. So the S is not sulfur. The C with an S is telling you the state of the carbon. So it is a solid. So if you see something in parentheses, kind of like in a subscript form, that's all it's telling you is what the state of that substance is. So oxygen is a G, so that is gas. Okay, so O2 exists as a gas. Notice that heat is released, so heat is sometimes written above the arrow. Sometimes it'll actually be written over here because when you burn charcoal, it gives off heat. So heat is like a product. Carbon dioxide is also G, so that means it's a gas. And that's why as the charcoal disappears, you don't see anything because it's making something that's a gas. And so that is being released into the air and you can't see it. So the other ones is sometimes you will see water and you might see an L like this. That's water as a liquid. Okay, so that's a common one for water. You could also sometimes see NaCl and it says this. AQ is aqueous. That means that salt is dissolved in water. In the human body, almost all reactions take place aqueous, right? Because water is the universal solvent. So everything, all of your sugars, all of your nutrients, your waste molecules, everything's dissolved in water in the body. So AQ, don't let that throw you. It just means that that substance is dissolved in water. It's still participating in the reaction. It's just dissolved. So this leads us to the topic of balancing equations. So a chemical equation, remember I said, is whatever reactants, they're either combining, breaking down, swapping partners, whatever they're doing, the arrow is always sort of the divider. Everything over here, these are always reactants, and I might have one thing, two things, I could have five things. Anything to the left of the arrow is a reactant. Everything that is to the right of the arrow is a product. So the arrow is sort of the divider. So there is a rule. There is a rule called the law of conservation of matter that says the total number of each atom on both sides of a reaction have to be the same. So like in that previous reaction, I can't just gain carbon or lose oxygen in the reaction. The total number of carbon and oxygen on both sides has to be the same. So this is just the same exact reaction. Charcoal, carbon, plus oxygen reacts to form carbon dioxide, CO2. So when you look at this reaction, do you see that the carbon, there's only one C in the formula? That on carbon dioxide, there's only one C in carbon dioxide? So those are actually balanced. What about the oxygen? So on the reactant side, I have O2. That means that there's two oxygens. But if I look at CO2, how many oxygens there? Two. So do you see that this is actually balanced? One carbon plus one oxygen molecule makes one carbon dioxide. So the coefficients for this one would all be 1, because 1 carbon plus 1 oxygen would make 1 carbon dioxide. So they call that number you put in front a coefficient. And it's referring to how many of the molecules that I have. So I would say 1 carbon plus 1 oxygen, even though oxygen's O2, I'm saying 1 oxygen molecule would form 1 carbon dioxide. So let's look at this one, the next one. Mg plus N2 makes Mg3N2. So if you have done balancing equations and you can do them just by looking back and forth, have at it. If you're like, I'm not sure about this, okay, follow the steps. First step, number 1, always draw a line down the arrow because that splits left and right. Right? So that's going to tell us the difference. Then you list the number of atoms based on the formula. So how many magnesiums on the left? Mg on the left. Just 1, right? So if I have just Mg, then I know that that's 1 magnesium. How many nitrogens based on the formula? 2. So that's on the reactant side. Then you go to the other side of the arrow and you list the same ones on the product side. So Mg3N2 has 3 magnesiums and 2 nitrogen. Does anybody not see where those numbers come from? So these are coming from the formulas. So the rule, law of conservation of matter, says total number of magnesiums on both sides has to be the same. Total number of nitrogens have to be the same. I can't change the formula. Like I couldn't just put Mg3 over on the left and be like, there. Okay? Because Mg just exists as a single atom of magnesium. So I'm going to put a number on the coefficient, look at the 2 sides, find 2 that are not the same. So in this, the magnesiums don't match, right? So the magnesium's 1 and 3. I'm going to have to put a number on the line in front of the magnesium that's lower to make it equal to the one that's greater. So what do I need to put here? So I'm going to have to multiply. So how many magnesiums would I need? I'd need 3 of them. So that 3 will multiply the total number of magnesiums by 3. So the coefficient is always going to multiply the numbers that you have in that formula. But notice it didn't change the nitrogen. The nitrogen is a different molecule. So just because I multiplied magnesium by 3, I don't have to multiply nitrogen by 3 because it's got its own line. It's its own separate molecule. So do I have to change anything else? No. Can you see that now magnesium is 3 and 3? Nitrogen is 2 and 2. So these would just be a 1. So if you don't change the numbers, they're just a 1. Sometimes I have people that want to put a 0 because they're like, well, I didn't have to do anything, so it's a 0. No, if you didn't have to do anything, then that means it's a 1. And it doesn't matter to me. You could just leave it with the 3 and leave the other ones blank. I always go back and like check my numbers, so I'll go back and put a 1 just so that I know for sure that I didn't mix them. Okay, so let's look at the next one because this always freaks people out. First thing you're going to do, draw a line with your arrow. And then the first thing you look at is Al2 parentheses CO3 parentheses 3. What does parentheses mean? Go back to the math. So it means that everything inside the parentheses is multiplied by the number outside. Okay, so how many aluminum? 2, because it's not inside the parentheses. So you see that's 2 aluminum. Now how many carbon? 3. So there's 1 inside. I got to multiply it by the number outside. So I got 3 carbons. How many oxygen? Nope, 9. Got to multiply. So 3 oxygens inside times the 3 that's outside. So that's 9 oxygen. That's it on that side, though. Go over to the other side. So over on the other side, I have Al2O3. So that's how many aluminum? 2. 2 aluminum. How many oxygen? 3. Then go over to the carbon dioxide. So CO2 has 1 carbon and 2 oxygens. So even though there's oxygen in 2 places on this side, don't link them together. Like don't list them together because they're in separate molecules. Okay, so I have oxygen in the aluminum molecule and oxygen in the carbon dioxide molecule. So you got to list them separate. But what I would do is take and put a little bracket so that you remember the total number of oxygen at the end have to be equal. So here's your next rule. So 1, draw a line. 2, list. Okay, if you have any parentheses, the number outside multiplies any inside the parentheses by that number. Third rule is balance the simplest atoms first. And by simplest, I mean the atoms found only in one place on either side. So see how aluminum's only in one place on each side? See how carbon is only in one place on each side? Balance those first. Always leave the ones that have a bracket to the end. Because oftentimes when you balance the simple ones, it'll balance the more complicated ones all by themselves. So aluminum, what do I have to do? Nothing. That's right. Aluminum's 2 and 2, so I'm done. So now I'm going to balance which? Carbon. So carbons are not balanced. So which side do I need to change? The right side. What do I have to put on this line? A 3. I have to put a 3 here because I need 3 carbons. So I have to multiply the carbon and the oxygen of the CO2. Both get multiplied by 3. So now I got 3 carbons and I have 6 oxygens. So do you see that because I put a 3 on that line, everything after that coefficient gets multiplied? So I have to multiply the carbon times 3 and the O2 times 3. Okay, did I mess up my aluminums? And I always go back and try to check those. I didn't change the aluminums. Carbons are balanced now. Okay, so now we have to balance oxygen. And what do you see? So I have 9 over on the left. How many total on the right? I have 9. Do you see that? So do you see that I've got 3 and 6? So I have 9 oxygen here. The total number of oxygens are balanced. So those blanks, I don't have to do anything. So those are what? 1s. So those would just be 1s. Okay, so next slide, same thing. Draw a line, make the list. Okay, so H2O has 2 H's, 1 oxygen, and 1 sodium. Right? Not if you've already gotten it.
I left my book bag at work.
So you can take the periodic take that PowerPoint if you need it, and there's a periodic table.
Get this?
Yeah, if you need it.
Yeah. Just what's the matter?
Okay, and then going on the other one, so H2 is 2H, 1 sodium, 1 oxygen, 1 hydrogen. So are there any found in more than one place? Which one? Yep. So just do this. So link those, right? Just so that you remember. So now with this one, there's sort of a trick, and sometimes when you come upon, you'll find that you have these odd even groups. So notice sodium, already balanced. Oxygen, already balanced. Right? So the only one that's not balanced is hydrogen. So do you see on the left, hydrogen is a 2? So that means it's either going to be a 2, a 4, a 6, an 8. It's going to have to be an even number. So I need to make the right side so that the total is an even number. So I want to change one of the molecules on the product side. The one that only has 1 hydrogen, I want to make sure that it's a double. Right, so that it ends up being even. So which side on the right will I change? Will I change the H2 or the NaOH? Change the NaOH. I need to make that an even number of hydrogens. So how many NaOHs would I need? 2. So if I put this 2 here, it's going to multiply my sodium by 2, my oxygen by 2, and my hydrogen by 2, because now I'll have an even number of hydrogens on the right that I can balance on the left. Because when you have the odd even, I'm going to have to make them both even. The only way they'll work. So this is, and I know that this messes up everything. That's the part that people go, but wait, I don't want to do that. That wrecks the sodium and it wrecks the oxygen. That's okay. We'll fix it. We've got to make sure, since hydrogen is an even number and an odd number, I've got to make them so that they have the same number, or at least that that I can balance them even numbers to get it to balance overall. So now I got 2 sodiums and I've got 2 oxygens and I've got 2 hydrogens. Okay. So now that I did this, go back and balance the simpler. So which one is the simpler? Which would you go back? You got to pick one, right? So you're just going to balance one of the elements on each side. And notice that oxygen's in one place, sodium's in one place. So I'd go back and balance those and then worry about balancing that hydrogen at the very end, always. Anything found in more than one place, balance it last. So if I go back and balance the oxygens, which side do I need to change? The left. So what do I have to put? 2. Because I have 2 oxygens on the right. So I'm going to have to multiply water times 2. So that means that's going to double the number of hydrogens and the number of oxygens on the left side. So now I have 4 H's. I have 2 oxys. Am I done?
No.
What else do I have to do?
So
So I got to balance sodium. So if I go to balance sodium, which side do I need to change? The left. And what do I need to put? 2. So if I put 2 in front of the sodium, remember that multiplies the number of sodium times 2. So 2 NAs. Then double check. Do I have 2 oxygen, 2 oxygen? Yes. 2 sodium, 2 sodium? Yes. Total number of hydrogen on the left is 4. Total number of hydrogen on the right is 4. Okay? And so that one that I didn't put anything, this is a 1. Okay? We're doing another one. So Al2SO4 parentheses 3. So remember what that means. Step 1, put your line. Step 2, you're listing how many atoms in each molecule. So Al2SO4 3 has how many aluminums? 2. How many sulfurs?
what is it? 1 or is it 12?
No, so think SO4 parentheses 3, everything inside is multiplied by 3, so that's 3 sulfurs. Okay, because remember in math, anytime you have parentheses and a number outside, everything inside multiplied by that number outside. So how many oxygens is that? 12. Right, because it's 4 oxygens times 3 gives me 12. And then I got to list how many in for water. So H2O is 2 hydrogens and 1 oxygen. So now I've got these. Those 2 oxygens on that side that's going to get bracketed. Let's go over to the other side. AlOH3 is what? How many aluminum? 1 aluminum. How many oxygen? 3. And how many hydrogen?
3.
And then do H2SO4. How many hydrogen? 2. How many sulfur?
1.
And then how many oxygen? And notice I write oxy because otherwise 40 looks like 40. So that's why I just have always written OXY, just because it helps me see it's oxygen and not a 0. So you can write it, if you can keep your O's and zeros straight, have at it. Okay, now I'm going to bracket the ones. Remember, I've got to list them singly. Even though there's oxygen in 2, I'm going to have to connect those. Right? So remember that those oxygen total are going to have to balance. What else is found in 2 places? Yes, the blasted hydrogen too. Okay, so the rule is, what are you going to balance first? Which ones? Aluminum or what are found in single? Sulfur, right? Notice that aluminum is only found in 1 place on either side. You can balance that one. Sulfur is only found in 1 place on either side. Balance that one. always balance the ones that you find only in one place on each side first. Then if I have to balance the more complicated, I would balance the hydrogen next, because notice hydrogen's only in one place on the left, 2 places on the right. So I would do that one third. I'd do oxygen last. Notice that oxygen's in 2 places on both sides. Hopefully, the oxygens will just balance themselves. Usually, if you balance the simpler ones, the harder ones will balance themselves. So, which one do you want to do? Okay, so which side am I going to change? The right. What number do I have to put on the line? Because remember, the coefficient, I have to multiply everything in that formula by that number. This is going to give me 2 aluminums, but it's also going to give me 6 more oxygen, and it's going to give me 6 hydrogen. So now my aluminums are balanced. It didn't fix anything else. But what am I going to balance second? So now I'm going to balance the sulfur. Which side am I going to have to change? The right. And what do I have to put on the line? A 3. So notice I have 3 sulfur on the reactant side, only 1 on the product side. So that means I'm going to need to put a 3 on this line. Everything after that number is multiplied by 3. So that means this hydrogen, this sulfur, and this oxygen, these are all multiplied by 3. So 2 times 3 is 6 more hydrogens. 1 times 3 gives me 3 sulfurs. And then 4 times 3 gives me 12 oxygens. Seems like a lot. Okay, but in doing that, double check your simple ones. Aluminum are balanced, right? 2 and 2. Sulfurs are balanced, right? 3 and 3. Okay, so now let's balance hydrogens. Okay, because hydrogen is only found in one place on the left. So that one we're going to balance before the oxygens. So on the left, I have 2 hydrogens in the water molecule. Over on the right, how many do I have total? 12. So does everybody see that? I have 6 and 6, so I have 12 hydrogens total. So what do I have to put in front of the water in order to have 12? I have to put a 6 here. So I need 6 waters. That means this is times 6, this is times 6. That will give me 12 hydrogens, and that'll give me 6 more oxygens in my pile of oxygens. And it looks like a pile. I did not mess up aluminums doing that. I did not mess up my sulfurs doing that. Now I have 12 hydrogens and 12 hydrogens. How many oxygens total on the left? 18. How many oxygens total on the right?
6.
And?
18.
I have 18. Done. So see this one? This and this is 18 oxygen. And this and this is 18 oxygen. So that's why I say balance the simple ones. Balance the ones that are only found in one place on either side. Most of the time, not 100%, but most of the time, the harder ones, the ones that are found in 2 places on each side, they'll just balance themselves. So I have one thing I didn't put. That means this is a 1. If I don't have to put a coefficient, it means it only took one of those molecules in that balance reaction. Okay, we're going to try one more, and then I have a set. I have this, so you can practice this. In fact, on your balancing equation sheet, so the same page that you have your periodic table handout, so this one, look, I have a whole 2 pages. So if you're like, I think I'm starting to get it, you can practice. So here is a page, and here's a whole another page. So there's about 40 balancing equation sheets. The answers are in Moodle. So if you go to the exam 1 module, the answer key for this is in Moodle, so you can go back and check yourself. So if you're like, I think I'm getting this, then you can actually check your answers to see if you are. Okay? And if you run into problems, if you have any other questions, like, we can run through a couple of them. But this is the one I'm going to leave you to practice. We'll do one more. So chlorine plus water makes HCl and O2. Okay? So in this, remember the steps. 1, draw your line. 2, list the number of atoms based on their formula. Cl2 is 2 chlorines. H2O, 2 hydrogens, 1 oxygen. Go over to the other side. 1 hydrogen, 1 chlorine, 2 oxygens. So when I look at this, nothing's balanced. But they're all simple, right? There's none found in more than one place. You can pick whichever one you want. Okay? So you try this. You pick an atom and see if you can balance it. Then balance the next one, and then try to balance. Now, sometimes when you balance two, it messes up one you just balanced. That's okay. You just have to go back and rebalance them. Like, don't let that, it doesn't mean you did the whole thing wrong. If you balance one and you go to balance the second one and it messes up the first one, that's okay. You may have to change that coefficient. So if you like start off with a 2 and then you have to multiply it times 2 more, we'll just change that number to a 4. Okay, so you may have to go through and multiply by more than one number. Just make sure your coefficient is the product of those. So in this, in each case, always list the atom in each molecule first, down the left, down the right. Starting with the simplest atoms, balance those first. Leave the ones that are found in more than one place on either side, leave those till the end. And remember, when you get done, if any have no lines, nothing on the line, then you know those are just ones. So which did you balance first, or try to? So you tried to balance the right. Which one did you balance? Hydrogen, chlorine, or oxygen? Okay, so you chose the hydrogen. So you're going to change. So in this one, the hydrogen on the left, there's 2. Hydrogen on the right, there's only 1. So what number did you have to put in front of HCl? You put a 2 times 2 times 2. Yep, so you're like, okay, I got the hydrogens right. Then what did you try to balance? The chlorines or the oxygen? Oxygens. Okay, so if the oxygens over on the right, there's 2. Over on the left, there's only 1. So what do I have to put in front of water? So I'd have to put a 2 in front of the H2O. That's times 2 and times 2. So this gives me 4 hydrogen, and this gives me 2 oxygen. So now my oxygens are balanced, okay? And my chlorines are balanced, but what happened to my hydrogens? They're not balanced. So I've got to go back to whichever one's smaller, I got to change. So on the left is 4 hydrogens. On the right is only 2 hydrogens. So what do I have to change that coefficient to make 4? So I'm going to have to multiply this times 2 more, which means times 2 times 2. That's now going to give me 4 hydrogens and 4 chlorines. Okay, what did I do now? So my chlorines aren't balanced. My oxygens are and my hydrogens are, but now my chlorines are not. So how do I balance the chlorines? Over on the left side, I've got to put a 2. That means times 2 is going to give me 4 chlorines. So see how I had to do that twice? If you have to do that at the end, that means this is a 4. Okay, and it's fine. So if you have to multiply it one time and you have to go back and you have to increase that number, just multiply it by whatever factor you have to. When you get done, both of those multiply each other. So I did times 2 again, so that would be a total of 4. And notice I didn't have to do anything to oxygen, so oxygen is a 1. Okay, I didn't have to put any number in front of that coefficient on the far right side, so that meant I only needed to use 1 oxygen in the balancing. Okay, so these ones really, some practicing. Okay, there's questions in the book they give you. I've got this one, here's another one. You've got like the whole double-sided page. So you've got like plenty of ones to practice with to get these ones. Once you get used to it, like if you haven't really done this, or if it's been a very, very long time, then just this practicing, you'll start to see there's kind of a pattern to it. But I always say the simplest thing to do, balance the singles first, then balance the more complicated. And 9 times out of 10, the complicated oxygens will balance themselves. It's almost always the oxygens. Almost always. Like, see this, well, no, that one's only got 1. These ones aren't too bad because they're only just 1 on each side. Okay? So we're going to introduce the whole math thing now. Okay, so we've balanced, we've talked about classes of matter, we've talked about states of matter. So this whole middle part of the section goes back over metric. So maybe you remember having metric in school. Maybe it's been a while. Maybe you were sort of like, that like went past. Okay, everything in chemistry is measured in metric. We don't measure in English units. We don't measure in ounces and pounds. We don't measure in dozens or feet or inches. Everything is done in metric. And in fact, it's easier. And all countries in the world use metric except us and some parts of England, some parts of Australia. And that's it. And the only reason the Australians do that is because they used to be a British colony, and that's why they kept the English, because English units were all developed in England. Okay? So in this, with math under metric, you have just base measurements. The base measurement for mass is called the gram. And they use an abbreviation lowercase g. The base unit for volume is the one that we are most comfortable with because they came out with 2-liter bottles of soda. And that is why people know, oh, I know what a liter is. Because I know it's like a half a bottle of soda. That's the one that everybody's like, yeah, okay, that one's not too bad. The base unit for length is the meter. And they use lowercase m, lowercase g for gram. Liter is a capital L. So there's one where I'm like, that's a little backwards. Like, they should just choose one. But no, okay? If I want to show anything larger or smaller than these base units, I use what they call a prefix. So when we're talking about length, you have a foot. But then you could talk about increments of a foot, which is inches. Or you could go larger increments and you'd have to know to go to the yard. And from the yard, you could go to a mile. But in order to know the difference, you have to remember what those number values are. You have to know there's 12 inches in a foot, that there's 3 feet in a mile, and that there's an awful lot of feet in a mile that I can't keep up with. But here, we only actually have to remember certain prefixes, and they apply to all of the ways of measuring. So if I'm talking about mass, volume, or length, I can use the same prefixes. In fact, for me, there's really just these. Kilo, deci, centi, milli, and micro. There's only 5. I really don't use nano. We really don't use mega or giga. So these are just 5 prefixes. If you can learn these 5 prefixes, you can convert from one form to another easy and never get them wrong. So kilo. Kilo is special because kilo is 1,000 times larger than the base unit. So if I want 1 kilogram, that is going to equal 1,000 grams because kilo is bigger. So kilo is like 2.2 pounds, whereas a gram is like a teaspoon. So it takes like 1,000 teaspoons to make a kilogram. So I'd have to weigh out 1,000 of those to get to the kilogram. Same thing though, if I had 1 kilometer, that's 1,000 meters. So kilo is always 1,000 of the base units. Last one, if I have a kiloliter, I'd have to have 1,000 liters. So they're equal. 1 kiloliter and 1,000 liters, they're equal. So they're saying the same thing, just like 12 inches in a foot is saying the exact same thing. They're just different measurements. These two are saying the exact same thing. The other 4 are all smaller. So the other 4, deci, centi, milli, and micro, I'm going to have a lot of the prefix units in order to make the base unit. So deci, I always think of deci as a decimal place, right? So a decimal place is just by a factor of 10. So it takes 10 deci to make a base unit. So the term deci is 10 times smaller. So 10 decigrams is 1 gram. 10 decimeters is 1 meter. 10 deciliters is a liter. So whenever I have deci, I get a 10 in front of the deci. The base unit gets the 1. the base unit being the gram, the meter, or the liter. So now centi, milli, micro, same thing. I think of century, which is 100 years. I also think of the number of pennies in a dollar, 100. So when you think of cent, think of centi, think of 100. So centi is 100 times smaller. So it takes 100 centigrams to make a gram, 100 centimeters to make a meter, and 100 centiliters to make a liter. So see how centi gets 100 in front of it? So if I have to do a conversion with centi, anytime I put centi, doesn't matter if it's centigram, centimeter, centiliters, centi would get 100. Milli, think of the millennium, right? So that's 1,000 years. So milli is 1,000. It takes 1,000 milligrams to make 1 gram. Milli is 1,000 times smaller than a base unit. 1,000 millimeters to make a meter. 1,000 milliliters to make a liter. So if I'm going to do a unit conversion with milli, milli always gets 1,000 in front of it. The base unit gets a 1. So in this, when they did mega, they made it a capital M because mega is really big. When they did milli, they made milli the little m. So now we used a capital M and a little m, and then you get to micro. So why they couldn't have picked a different word, I don't know. But it's another one of those Latin things. So when they got to micro, they went to the Greek term mu. So do you see what the U looks like? It looks like a U with the foot on the front. That's actually what the symbol looks like. That symbol is actually the Greek symbol mu. Just think of it as it's a U with a foot on the front. Okay? So when you see that funny U, that's micro. And micro is 1,000,000 times smaller. And I always think of a microscope because when you look at things through the microscope, you can look at them at up to 1,000,000 times their normal size. So it will take, 1,000,000 is a 1 with 6 zeros. 1,000,000 micrograms makes 1 gram. 1,000,000 micrometers to make 1 meter. And 1,000,000 microliters to make 1 liter. So do you see that deci, centi, milli, micro are very similar? Deci, it takes 10 deci to make a base unit. It takes 10 deci to make a gram, meter, or liter. With centi, it takes 100. So centi gets the 100 in front to make 1 base unit. Milli is 1,000 to make a base unit. Micro is 1,000,000 because those are all smaller. So the base unit always gets a 1 when we say how they're equal. And whatever the prefixed unit of deci, centi, milli, and micro, those are going to get 10, 100, 1,000, 1,000,000. The only oddball in this is kilo. So with kilo, you need to remember that kilo always gets the 1. And it takes 1,000 base units to make a kilo because kilo is a big number. So for like kilometers, a kilometer is almost just over a half a mile. So you know a meter is this long. Okay, like a meter stick, it's a little longer than a yard. So a meter is this long. It takes 1,000 of these to make a kilometer. So the base unit will always get the 1,000 if kilo is involved. So that's one to put in a note for yourself. Kilo always gets the 1. The base unit gets the 1,000. But with all the other ones, deci gets 10, centi gets 100, milli gets 1,000, micro gets 1,000,000. So if I want to convert from one unit to another, those things are all I have to remember. I have to remember what kilo, deci, centi, milli, and micro mean. Those 5 things. If I can remember those 5 things, I can convert in any measurement. I don't have to remember how many ounces in a quart. I don't have to remember how many feet in a yard. I don't have to remember, what was the other one? How many quarts in a gallon. I don't have to remember any of those numbers. All I have to remember is what is the equivalent of the prefix unit to the base unit. So in this one, if I want to figure out I need to use deci and grams, I just need to remember that it takes 10 decigrams to make 1 gram. So remember in this one, right here, 10 decigrams is equal to 1 gram. So that means I can put them on top of each other because they're equivalent. 10 decigrams over 1 gram, saying the same thing, just different units, or I could flip it and put it the other way. And one way you can think about this, you will agree that 12 eggs and 1 dozen are the same, right? That's all this is saying, is this is just converting. So if I say get a dozen eggs or 12 eggs, you know that's the exact same thing. So if I say measure out 10 decigrams or 1 gram, you know they're exactly the same. It's just using it in a different unit form. So they call these a conversion factor. So a conversion factor can allow you to go from grams to decigrams or decigrams to grams. And you can set it up so that units will cancel. That's the reason for keeping units and following them this way, is that you will always do them correctly. Some students use like the number line, like they remember how to like convert in metric by a number line. But if you leave out one of your letters in a number line, you could be off by a factor of 10. Or sometimes a factor of 1,000. You could be off by a lot. So this way, you will set it up. All you have to remember are those 5 things. So here's the steps. So let's say that I have 12 milliliters, and I want to know how many liters is that? Right? So the given unit is what I always start with. Okay, so that's the number that you know, right? So that's the 12 milliliters. I'm going to put my 12 milliliters here, 12 milliliters times, and then you're going to put a line. I need to put the unit I'm given on the bottom, because what do those units do when you multiply? If I have milliliters on the top and milliliters on the bottom, they cancel each other. Okay, so I'm going to put milliliters down here, and the answer that I want is liters, so I'm going to put that on the top. Now, all I have to remember is milli and the liter. Milli gets a what? Look back if you need to. Milli always gets a, it's like the millennium. How many years? 1,000. So this is 1,000. So 1,000 milliliters is equal to 1 liter. So in this, notice that milli always gets the 1. The base unit, milli gets the 1,000, the base unit gets the 1. This is going to allow milliliters and milliliters to cancel, and then I just have to do the math. So I just take 12 times 1. You know, anything times or divided by 1 doesn't change it. It stays exactly the same, so you can ignore that 1. But 12 divided by 1,000, because this would be like 12 mils, times 1 liter over 1,000 milliliters. Milliliters and milliliters can cancel. So it would be 12 times 1 divided by 1,000. Moving the decimal place, it would go to the left by the number of zeros. I have the calculators. If you don't have a calculator, you may want to come and grab one. Oh, you don't have to come and get one because I'm going to quit. I got hung up talking about it. All right. So this would be 0.012 liters. Okay, everything across the top, divide by the bottom. So what we're going to do, and you can practice these ones, see if you can set them up. It's exactly the same. I even put the units that like what you need to remember at the very top. 24 milliliters is how many liters, 97.1 grams is how many kilograms, 125,000 micrometers is how many meters. So see if you can convert those. We will do these ones on Wednesday. I've got a couple of other ones to practice, and then we're going to go on to like significant figures and rounding, okay, to finish up the math in this chapter.